Hi, my name is Brian Tang. I'm an associate professor in the Department of Atmospheric and Environmental Sciences. I'm happy to be able to share with you some of the research that I do. In the geosciences, you see lots of pictures of maps. This map, in particular, is one that I like to show. In that circle you see, there are more people living inside of it than outside of it. Extreme weather, like tropical cyclones, such as the typhoon you see pictured, and severe weather, such as the hail you see pictured, can be especially impactful on certain populations in Asia and the Pacific Islands. Also, the effects of climate change, such as rising sea levels, pose a looming and major problem for low-lying communities along the coast and entire Pacific Island nations. Understanding and predicting extreme weather and climate change is important for mitigating the risks they pose. I like to think of weather and climate as one of the great unifiers of the world. All of us are touched by it. National and global economies are all sensitive to it. The same images of a tropical cyclone, hail, and sea level rise can be moved over other parts of the world. We deal with the risks and vulnerabilities from the exact same phenomena. In particular, the grand challenge of climate change is something the world will have to tackle collectively, or risk facing a global tragedy of the commons. Let me delve into some of the specific extreme weather phenomena that I study, and some of the research questions that I am exploring. One of my research areas is tropical cyclones, such as pictured in this satellite image of a hurricane spinning off the coast of Cuba and Hispaniola. Some questions that form the basis of my research are: 1. How do tropical cyclones form? 2. What causes tropical cyclones to rapidly intensify, which can be especially dangerous if that happens ahead of landfall over a populated area? And 3, how does the environment interact with tropical cyclones? One particular interest is how tropical cyclones weaken due to wind shear, where the wind steering a tropical cyclone change in speed and direction with height. Another one of my research areas is severe thunderstorms, which produce high winds, large hail, tornadoes, and flooding rains. This radar animation shows a severe thunderstorm in 2014 that passed through Amsterdam, New York, and Duanesburg, New York, just west of the Albany area. This particular severe thunderstorm produced hail as large as softballs, and a tornado that destroyed and damaged several houses. One question that I'm interested in is: how does terrain affect severe thunderstorms? Additionally, I have done some work looking at long-term trends in large hail across the United States, and have found evidence that large hail is increasing in frequency, which might be contributing to increased hail-related property damage and losses over the last few decades. In my research on both tropical cyclones and severe weather, we use a variety of tools to perform the research, such as observations, theory, and computer modeling. One of my main tools is a simple computer model of a tropical cyclone. Presume we wanted to simulate a generic tropical cyclone. Given that tropical cyclones are roughly circular and spin around a well-defined center, we can construct our computer model using a cylindrical geometry. In my model, I am simplifying things further by assuming axial symmetry, such that the system of equations is only a function of radius and height. We can visualize the model output in this radius-height geometry as shown here. The blue shading shows the tangential wind speed, or the winds going around the center. The gray shading shows clouds, and the green shading shows rain. Let's look at an animation of this simulation. We initialize this computer model with a weak initial vortex just to get it going. Eventually, you see clouds begin to form. Some rain falls from the clouds. it seems random and chaotic, like bubbles rising from the ground, as the heat and moisture taken from the underlying ocean is transferred up into the atmosphere through these clouds. For a while, it is tough to see how this tropical cyclone is going to develop and strengthen, but the process is pretty quick. Around 80 hours, you see the wind speed start to increase, with the darker shades of blue appearing. By the end of the simulation, you see one dominant cloud and a coherent area of strong winds stretching from the surface. The signature of a well-developed hurricane. We can use models like this to understand the physics and thermodynamics involved in tropical cyclone formation and intensification. So that's a little bit about my research. Thanks for listening in.